Alright, hello everybody. So today I'm going to finish off Redox, and I'm going to talk to you a little bit about, with Redox, some of the electrolytic cells that I didn't touch upon yesterday. And yesterday we finished off with electroplating, and we talked about how to electroplate cells. Today we're going to finish off with electrolysis, or electrolysis. And what we're going to do with that is show how you can isolate elements from a compound. And what we like to do with isolating elements from a compound really is to try and get those elements that are really reactive by themselves, so that this way, if we want some sodium, for example, we try to find it in nature. We can't find it in nature, so what do? We use electricity to isolate sodium from a compound like sodium chloride, and that will allow us to have sodium. We can then store it under really inert conditions where it won't react with anything, and then we get it here in the lab and we can throw it in water and see it explode, or we can use it as a coolant in a nuclear reactor. We can do what we need to do in order to, have pure sodium. So yesterday I went over electroplating, and we'll actually do this lab in class. So you'll get to see a key electroplated. The idea, again, is to have an expensive metal as the anode. That metal's oxidized. The metal becomes ions. Those ions will be attracted to the negative cathode, which is the object you want to plate. Those positive ions will then bind to that negative cathode and actually form a coating of solid metal on top of a cathode. Okay, so that is electroplating. Here is another example of electrolytic cells called electrolysis. And what I show you here is that we have basically a pool of molten sodium chloride. And that's really important for you to see in this particular case, that the Na and the Cl, that is actually molten. This is a liquid. And so what we do is we have an anode and a cathode. The anode is going to be positively charged because it's attached to the positive terminal of the battery. The cathode is negatively charged. It is attached to the negative terminal of the battery. If you ever want to find what the cathode and anode is in an electrolytic cell, you really should look at the voltage source. Follow the positive end of the voltage source, that will go to the anode. The negative end of the voltage source will go to the cathode. Now here on the left, I show you pure molten salts. That's the first thing, and that's over here. If we have pure molten salts, the salt exists as ions, liquid ions. The Na positive ions would be attracted to the cathode, and look at what happens at the cathode. We get solid or liquid sodium from a reduction of sodium ions. If we look at the chlorine, it starts off as chloride. It is attracted to the positive anode, and it is oxidized to form chlorine gas. What I have here is my isolated elements, my liquid sodium, and my gaseous chlorine. There's no water here at all. If I had water, then there'd be a competition, and we'll see that below, and I'll actually do electrolysis of an ionic salt, not sodium chloride, because it really won't work well, but I'll do an electrolysis of an aqueous ionic salt, and you'll see what happens. We'll talk about that in class. Now, what if I wanted to get hydrogen and oxygen? What I could do is I could do water alone in an inert electrolytic solution. Generally, you would use something like 0.1 molar H2SO4. This itself, this does not undergo electrolysis, so no electrolysis here. Oops, sorry. Come on. No electrolysis. Instead, the water is electrolyzed, and you would produce oxygen at the anode, that's an oxidation, and you would produce hydrogen at the cathode, that's the reduction. Now what happens is, and I alluded to this, is I gave you two examples up here, molten salt, where you could get back your sodium, for example, and your chlorine from the salt, and then I could have my water, where I have my pure water with something that will not undergo electrolysis but will conduct current, and I can get my oxygen and my hydrogen. But what if I put a salt that kinda can be oxidized and reduced in water, and the water itself can be oxidized and reduced? What you end up with is a competition. You end up with a competition for the current that's being applied. And so when we see this, If I were to put something like a group 1 or 2 metal or aluminum, and I were to have these ions in water, they themselves would not be reduced. If I put in certain metals like, cadmium, gold, silver, those could be reduced. If I try to reduce a halide in water, like fluoride, I can't oxidize fluoride. It's too stable. But I can oxidize things like iodide, and I'm going to actually show you that when I do the sample electrolysis. And polyatomic ions, if I try and reduce those in water, we can see that above up here with the sulfate. If I try and oxidize those in water, that won't work either. So, my best bet to get an electrolysis is to use the molten salt. I'll show you a good video of that where they do that. They take lead bromide and they actually oxidize and reduce it, and they get bromine and they get lead. If I have pure water, if I add an electrolyte to it that will conduct the electrical current, I can get H2 and O2. And if I want to, I could use a salt that's like potassium iodide, for example. I won't get potassium, it's too stable as an ion, but I will get iodine if I try and do that in water. Okay, this is just showing you an example of electrolysis versus voltaic. And the idea behind this is to show you that when your battery is charging, you're actually going against the normal discharge, the normal voltaic nature of the battery, and we're actually forcing the cell to regenerate, and we're actually causing the battery to become an electrolytic cell. When we discharge our battery, so we unplug it from the wall, and then we use the battery, at that point it will work as a normal voltaic cell. So, the last thing I want to talk to you about is oxidizing and reducing agents. They use this a lot on the SAT subject test. It's on the old Regents questions. Sometimes it's on AP/IB chemistry, and they use it in biology too. And an oxidizing agent, all it really does is it's just the substance reduced. They call it the oxidizing agent because it is responsible for oxidizing the other substance. But when I see oxidizing agent in a problem, I just say, if they say, what's the oxidizing agent? I just cross that out and I say, what is reduced? Same thing with reducing agent. It's the substance that's being oxidized. So if they ask me, what's the reducing agent? Then I would cross that out and I would say, what's oxidized? If they say, what's the best reducing agent? I'll cross that out and I'll say, what's most easily oxidized. Okay, so we'll do some of these. You'll see. When we did the multiple choice in class practice, I said don't do those. But really, the simple trick is to, if you see oxidizing agent, cross it out and say what's being reduced. If you see, excuse me, if you see reducing agent, cross it out and say what's being oxidized. All right, thanks so much for watching. This concludes our oxidation reduction videos. Thanks.